So we will carry on with our second talk of the morning and first of David's series. So David Damanik with gap labeling.
Okay, thank you very much. Also like to thank the organizers for the invitation and the opportunity to give these lectures here. It's a great pleasure to do so. So I was asked to talk about gap labeling, so I will do that. I should say that this is, for the most part, quite classical stuff. So most of the things I will explain are really from the 80s, but there have been some recent developments and I'll try to touch on those as well. Okay, so you will not be able to read the titles of my slides very well, but this one says the one-dimensional Anderson model. So the beginning of my talk will mostly just review things that you have likely already seen during the school, but hopefully you won't hate me for that. And I also want to set up notation and the context. Okay, so let's recall what the Anderson model is, and actually before explaining that, so it will be the one-dimensional Anderson model. Of course, some of the things I'm saying here will, of course, also be known and true for the higher dimensional case. So I should explain why I'm restricting to one dimension. So when you think of gap labeling, there are really two versions of gap labeling. One works in all dimensions, and the other one works in one dimension. So you would think it's, of course, better to talk about the more general approach, but I will not talk about the general approach. I will talk about the one-dimensional approach. Partly because the recent developments that I mentioned really were made based on this one-dimensional approach. And so this is in some sense not a surprise because, at least from my perspective, it's unlikely that you will have similar observations in higher dimensions. So I hope I will convey my excitement for the recent developments, which sort of explain why I want to introduce this alternative method, this alternative approach to gap labeling. Okay, so for that reason, I'm looking at the one-dimensional Anderson model. Okay, so the Anderson model is a random trading operator. So you have to pick a measure that determines the potential at a single site. And then you take the same measure to independently produce values at other sites as well. And so the collection of all these values that you get by drawing independently from this same distribution will form the potential. And so the distribution of the probability measure is called mu. So if I want to get an IID sequence where each component comes from mu, I have to look at this product measure, mu to the z. So this will be a measure on the sequence space, sequences with values in the support of mu. And so these sequences that you produce here that are in the bi-infinite sequences with values in the support of mu, I want to consider as potentials for Schrödinger operators, right? So I'm sure you've seen all these things before. So this potential v omega I put here, I put the discrete Laplace in here, and I get an operator in L2 of z. And so this is called the one-dimensional Anderson model. And so in this talk, I will almost exclusively, or maybe even exclusively, talk about the spectrum. I will not talk about spectral measures. I will not talk about quantum dynamics. I will just talk about the spectrum of operators. So now that I have these operators here, I can ask myself, well, what does the spectrum look like? And this is a classical theorem. This is from 1980 in a paper of Kunz and Suya that identifies the spectrum for mu almost every omega as this set. So first of all, the spectrum for mu almost every omega is equal to the same set. And they even tell you what the set is. It's the Minkowski sum of the interval -2, 2, and the topological support of nu. Okay, so what is the topological support? I already used it here. So this is a probability measure on R. The topological support is the smallest closed set whose complement has 0 measure, right? So this here is a closed set. And actually, I assumed the support to be compact. This is a compact set. And I take this sum of two sets. So really all the possible sums I can form by taking an element here and an element here. So this is really exciting. Well, first of all, let me show all the critical aspects of this result. So first of all, the spectrum is almost surely equal to the same set. But second of all, you actually know what that set is. It's equal to this specific sum of two sets. I'll come back to that point in a moment. And once you have this description of the almost sure spectrum, you can derive a conclusion. What's the conclusion? Well, you take each point on the support of nu. By the way, the Bernoulli case has support of nu equal to 2 points, for example. And so you take each point in the support of nu, for example, 2 different points in the case of Bernoulli, and you attach this interval of length 4. Okay, and then you basically attach this interval of length 4 to all points in the support, take the union of them all, and this is the almost sure spectrum. In other words, what you get is a set, well, this is compact, this will be a compact set, where each connected component has to have length at least 4. And so this in particular means you can have at most finitely many gaps. And in fact, gaps are produced by gaps between points in the support of length bigger than 4, because only then is implanting intervals of length 4 such that there's something left between them. All right, so here is a very nice situation where you can determine almost sure spectra explicitly. The proof is very short, and the 2 things that you use in the proof are the realization that for certain operators, it's easy to determine the spectrum. The types of operators for which it's easy to determine the spectrum that play a role in this proof are of 2 kinds. The first one is a Schrödinger operator with a constant potential. And the other one is a diagonal matrix, a bi-infinite diagonal matrix. Those are the 2 types of operators whose spectra are easy to determine. The first one, Schrödinger, Laplace plus constant, is just -2 shifted by that constant. And the spectrum of a diagonal operator, just the potential by itself, is just a closure of the set of the diagonal entries. So this is easy to see. And those 2 pieces of information are sufficient to establish this theorem. So now that I've recalled that, let me emphasize one more time. This interval here, -2 is the spectrum of the Laplacian. And this support of nu is the spectrum of the potential for mu almost every omega, because then you see all the points in the support and the closure gives you the support, the topological support. So in other words, not only is it explicit and has as a nice consequence the scarcity of gaps, it also has the interpretation of, well, the spectrum of the sum of 2 operators is the sum of the 2 spectra. It's really pretty. Okay, so that's what I wanted to say about the spectrum of the Anderson model. Now I want to recall the almost mature operator, which I'm sure has been talked about many times during these 2 weeks. So as in other talks, the notation is probably exactly the same. The coupling constant is lambda. The frequency is irrational and denoted by alpha. And the phase is omega. It's in R mod Z, which I'll write as T. That's the circle. And the potential is given by starting at omega in this circle, written in additive notation, adding on alpha and many times, plugging that into a certain function, and the function is 2 lambda cosine 2 pi argument. Okay, so you sample this function 2 lambda cosine 2 pi argument along the iterates of an irrational rotation of the circle, and that's the potential of the almost mature operator. So again, you generate this by infinite sequence, put it here, you get a Schrödinger operator in L2 of Z, call it almost mature, and you ask yourself, what does the spectrum look like? And this theorem also made an appearance in the previous talk. So this is the answer to the Damanik problem. There were many people who contributed. The final piece of the puzzle was provided by Avila Jitomiskaya. And the statement is that in all cases where the potential can possibly hold, where the result can possibly hold, the spectrum is a Cantor set. Okay, so what do you have to exclude? Exactly the case where the potential is periodic. Namely, you will get a periodic potential if lambda is 0. I mean, lambda can also be negative. And if the frequency is rational. So in the non-trivial case where you're not periodic, the spectrum turns out to be what's called a Cantor set. And by that, you really just mean a perfect nowhere dense compact subset of R. And the spectrum now is, so this Cantor set is equal to the spectrum now even for all omegas, okay? So the spectrum is not only almost surely constant, almost surely here would be to the natural choice of a measure on T, and the natural choice here is Lebesgue measure, you have no other choice. And so it's even globally constant. And this is really opposite to the topological structure of the spectrum in the Anderson model case. Here you have lots and lots of gaps. In fact, the denseness of the gaps persists even if you vary lambda and alpha through the allowed values, precluding periodicity of the potential. So this is a very persistent denseness of spectral gaps. Okay, so you've seen the Hofstadter butterfly, I'm sure, and even the colored version you've seen, I'm sure, because it's even on the workshop summer school poster. Okay, so you've seen this colored version of the Hofstadter butterfly. What's the difference between the two? Well, one is black and white and the other one is colored. No, that's not what I'm emphasizing. The difference is the following. Here you're plotting the spectrum, okay? Right, so here you have energy on the x-axis and you have alpha on the y-axis. So if you take a slice like this, you get the spectrum for the corresponding value of alpha. In truth, these are all these spectra for rational alpha, and in even more truth, those are unions over the phases of the spectra of rational alphas. But continuity property of the spectrum sort of suggests what the irrational spectrum will look like and really shows how you get more and more gaps as you go through a sequence of rational approximants to an irrational limit. Okay, so this picture emphasizes the spectrum, whereas this picture emphasizes the complement of the spectrum because it colors the components of the complement. And so the colors that you see here are very much related to gap labeling. So I hope I'll make that point later when I've explained what gap labeling actually is. So gap labeling is about labeling the gaps of spectra. So naturally, you're talking about the complement of the spectrum. And so this is what we want to discuss. Sure.
Or is it just to identify different gaps?
So so the if you have an alpha, then if you take any connected component of the complement of the spectrum, a gap, then I will explain all these things. The integrated density of states will take a constant value in that gap. And the gap labeling theorem tells you, I will hopefully explain that too, that this value will be of the form integer plus integer times alpha, where alpha is the frequency. And so now the colors, so okay, write that as as L plus K times alpha, and the colors correspond to K. Okay, so what happens here as you move sort of in this direction, the value of the IDS changes, but the multiplier of alpha doesn't. Right? It changes because alpha changes, right? But the integer multiplier of it won't change. Okay, so the colors correspond to integers. All right, so here are the general principles, which I'm sure were discussed in Jake's lectures, behind this almost sure constancy or constancy of the spectrum. So I'll go through that a little quicker, but this is done under the assumption that you remember these things. So whenever you feel I'm going too fast, let me know. I will immediately slow down. But I'm working currently under the assumption that I'm not telling you something you haven't seen before. Okay, so the framework for Jake's lectures were these dynamically defined potentials. So they're always of this form where you iterate a map T that maps from omega to omega, omega being a compact metric space. It's a homeomorphism, so you can also look at negative iterates. So n here really is in Z. So this T to the n omega is just the orbit of omega under this homeomorphism T. It's a sequence in omega. But now you apply this map F that maps in a continuous way from omega to R. So after applying F, you get a bi-infinite real valued sequence, which again defines a Schrödinger operator in L2 of Z, just as before. And so the two examples, the Anderson model and the almost material operator, of course, of this form. So in the almost material operator was very apparent. So omega there was the circle, and this function F was this 2 lambda cosine 2 pi times argument. In the Anderson model case, you also have that description. So the omega there is, I mean, I think I probably even wrote it down, is this topological support of nu to the Z, that's omega. And T is the shift transformation. It takes a sequence and shifts it over 1 unit. And so both these examples fit into this general framework. And there are two mechanisms that allow you to conclude that the spectrum doesn't change very much. So the first one is, well, if you have this dynamical system, discrete time dynamical system, omega comma t, you can ask whether you can find some ergodic probability measure. So I won't define that here. Again, working on the assumption that Jake defined that. So if you choose an ergodic probability measure, then actually the spectrum will be almost surely independent of omega. So the whole point of ergodicity is that invariant things are almost surely constant. The spectrum is invariant because if you shift, you have the same spectrum because the shift is a unitary transformation that leaves the spectrum invariant. So this is really a consequence of ergodicity. So the question is, which other ergodic measures and which one do I want to work with? So in some sense, before even looking for ergodic measures, you should ask yourself whether orbits are dense. So T is called minimal if every orbit is dense. So the orbits are these sets of points T to the n omega, n varies. If this is a dense subset of omega, then you can approximate anything you want. And again, the spectrum has a semi-continuity property. So the limit spectrum will be contained in the approximating spectra. And if every orbit is dense, you can switch roles between the approximating guy and the approximated guy. And so then you get both inclusions and you get equality. And the spectrum, therefore, just is entirely independent of omega. So the second theorem applies to almost material. The first theorem applies to the Anderson model. So that's really the general reason why these almost sure or sure spectra exist. Okay, so now that you have these almost sure spectra, sigma, so of course they depend on F and mu. They also depend on omega and T, but I sort of consider the dynamical system fixed, but I don't consider the measure and the sampling function fixed, so I indicate them here. So the first question is whether there are any gaps. Okay, so in the Anderson model, like I said, if the support of nu is such that it has no gaps of length bigger than 4, then the spectrum of the Anderson model is obtained by implanting these intervals of length 4, and that closes all the gaps if your original gaps were of length bounded by 4. So in that case, the spectrum actually has no gaps. It's connected. But sometimes, of course, there are gaps. And then you can ask yourself, are there finitely many? Are there infinitely many? If there are finitely many, how many? And if there are infinitely many, there still are two interesting cases. One is where the gaps are dense, as it is now known to be the case in the almost mature operator scenario. And there may also not be dense. So the spectrum, even though there are infinitely many gaps, could contain an interval. So all these questions sort of pose themselves if you have the existence of the almost sure spectrum and you're interested in its topological structure, its gap structure. Okay, so these questions naturally lead you to the consideration of gap labeling, because that's really the best tool that we have in this general context to study these questions. All right, so what is gap labeling? So we have our almost sure spectrum. What is a gap? A gap is really a connected component of its complement in R. That's a gap. Sometimes you discard the unbounded gaps, right? The half line above the spectrum and the half line below the spectrum, and you're really interested in the bounded gaps, but you can also include the unbounded ones. So those are the gaps. What is gap labeling? You want to attach labels. So as in your question, the labels there are of the form K alpha, really. So that will be the label, but where does it come from? So the first step in showing that there is a natural way to label the gaps is to introduce or recall the concept of the integrated density of states. So again, I'm sure you've seen that before. I will recall it. And so once you have the IDS and prove this fundamental result that the growth points of the IDS are precisely the points in the spectrum, you know that off the spectrum it doesn't grow, so therefore it's constant in gaps. But on the spectrum it does grow, so the values it takes in two different gaps are different. And so therefore, each gap has a constant value, and you get a one-to-one correspondence between the values you assign and the gaps. And those are the labels you want to use. Okay, so now we've labeled the gaps. And so now the next step is to understand what we're getting, right? So I just told you in the almost mature, it's K alpha. How do we understand that the values take the form K alpha? So that's the purpose of gap labeling theory. So the theory tells you why the values take the values they do. Okay, so and both versions of gap labeling theory date back to the 1980s. So the version of Belisa, that's the one I referred to before, works in all space dimensions. And it was developed between 81 and 83, something like that. So in the early 80s. So the other one is a bit later, that's from 86. Okay, so if you want to do that, you have to use K-theory of C-star algebras. So I won't write anything on the slides, but I want to say a few words. So if you understand that the IDS takes a constant value on a gap, and the values on gaps are different if you have different gaps, and you want to ask yourself why the numbers that you see, these constant values, have a certain form, then you have to use properties that somehow hold in the complement of the spectrum. What holds in the complement of the spectrum are many things, but what is the thing that's used to do K-theory of C-star algebras? It's the following. So if you look at a spectral projection, maybe I should write something. So if you have spectrum here and you have a gap here, right? And then you take an energy in the gap. And so if you look at, this object here. So H omega is a self-adjoint operator. The spectral theorem allows you to apply functions to the operator. The function that I want to apply is a characteristic function, namely of the interval from -infinity to E, where E is in the gap. Okay, so the the functional calculus tells you that the operator that you get here reflects certain properties of this function here. What properties does this function have? It's equal to its complex conjugate, and it's equal to its square. On the operator level, it tells you that this operator is equal to its adjoint and to its square. So this will be an orthogonal projection. Okay. The other thing that the functional calculus tells you that is that this operator doesn't depend on this full function. It only depends on what the function does on the spectrum. Okay. In other words, you can alter the function of the spectrum. And so, for example, I can shift the E back and forth. That doesn't change this function on the spectrum because I'm staying inside the gap. Okay, so this object is actually the same for all E's in the gap. The other thing is that this function, if I'm allowed to alter it off the spectrum, I can mollify. Okay, so now it's a continuous function applied to my operator. And that's important because these C-star algebras here that you associate with these operators here are really related to continuous functions of the operator. Okay, so therefore spectral projections can be viewed as continuous functions of the operator. And because of that, what happens in the C-star algebra is relevant. Okay, so the C-star algebra is sort of the smallest C-star algebra that contains your operators. That's what the C-star algebra will be. I won't even define what a C-star algebra is, but that's sort of the algebra. And then it comes with a bunch of K groups. The fundamental ones are K0 and K1. And so this really uses K0, and K0 studies the projections in the C-star algebra, but really in matrix algebras over the C-star algebra. Okay, so that's not that important. The important thing is that the K0 group really is related to projections. So operators that are equal to their square and adjoint in that C-star algebra. And this is one of them, okay? So that's precisely why spectral projections have something to do with the K0 group of the associated C-star algebra. And then Belisard's gap labeling theorem looks at a certain normalized trace on the K0 group of that C-star algebra, and the image is the one that will contain all your gap labels. That's his gap labeling theorem. So in some sense, once you have it, it's sort of natural, because just by this brief discussion here, it really has to lie in there, okay? So that's good as a general abstract result. But if you want to use it for something, you have to compute these K0 groups of C-star algebras. And that's a major undertaking. So for example, if you do the almost mature, you just have the irrational rotation on the circle. The associated C-star algebra is a rotation algebra, and the computation of its K0 group was a major result. I mean, people really worked hard to compute the K0 group of the rotation algebra. So if you want to do more complicated examples, it becomes even more difficult to actually compute these K0 groups of the relevant C-star algebras. And that's partly the reason why, at least from my perspective, this approach is difficult to actually exploit for concrete examples. But again, I mean, for some examples, it has been carried out. So I'm not saying it's useless, absolutely not, but it's difficult to implement. That's really why I want to advertise the other approach, because the goal of these lectures is to convince you that if you want to do explicit computations, the other approach makes things super easy. I mean, I will actually show you lots of computations tomorrow, and then you explicitly compute gap labels. And in some cases, these computations give you surprising consequences. So those are the recent developments I was referring to earlier. And so this refers to Johnson's gap labeling theory, and that's based on the Schwarzman homomorphism. So the Schwarzman homomorphism is a purely topological object. It has nothing to do with spectral theory. However, if you compute it, or rather its image or range, which is called the Schwarzman group, the gap labeling theorem will tell you that the gap labels are elements in that Schwarzman group. So there is this group that you can compute. And like I said, in many cases, it's not difficult to compute it. And so this will also be a way to interpret the numbers that you see here when you do the gap labeling. Okay, so I talked a little bit about K-theory of C-star algebras, but that will be the end of it. I apologize for that. So the rest of the lecture today will be devoted to the gap labeling theorem based on the Schwarzman homomorphism, and tomorrow I'll do examples. All right, so here is another slide that contains things that you surely have seen before. So the density of states measure is the mu average. Mu here is the ergodic measure on omega that you choose. You take the spectral measure corresponding to h omega and delta naught, and you average that against mu, and you get a new probability measure, and that's called the density of states measure. And the integrated density of states is the accumulation function of the density of states measure. So you integrate from minus infinity to e, and that's k of e. So because this is a probability measure, this will be a non-decreasing function that goes from 0 near minus infinity to 1 near plus infinity, right? So this is how you can and should visualize this function k of e, the IDS. So that's the first perspective on the IDS, but there's a second one, and both are useful. So the second perspective on the IDS is you take your Schrödinger operator, Laplace plus potential, and you restrict it to an interval of length n with Dirichlet boundary conditions. And now you get this tridiagonal n by n matrix, and it's easy to see. Well, first of all, it has real eigenvalues, but it's also easy to see that the eigenvalues are simple. So you get n eigenvalues of this matrix here that you can write down like this. And then you define a probability measure by placing mass 1 over n on each of them. And then you send n to infinity. And then you can show that for mu almost every omega, this measure here will converge weakly to the density of states measure defined on the previous slide by mu averaging the spectral measures of the infinite volume operator. Okay, so these are the two perspectives on the IDS. I'm sure Jake explained these things. So the first, where you average the spectral measures against mu, allows you for a very quick proof of this result. The topological support of the density of states measure is equal to the almost sure spectrum. And so this really means precisely what I said before. If you look at the integrated density of states, the accumulation function of this measure here, it will have growth points precisely equal to the elements of the almost sure spectrum. So in particular, it's constant on gaps and takes different values on different gaps. So that's good. So this tells us what I referred to before. If you just look at a gap of the almost pure spectrum and look at the constant value of K of E inside that, and then you can attach that value to the gap. And that's your labeling of the gaps. So now you have the labels. Again, the goal of gap labeling theory is to interpret the labels. And for that, the second perspective is relevant. The second perspective are these finite box operators, their eigenvalues, and how they accumulate on the infinite operator spectrum. Why? So the fundamental reason is oscillation theory. Oscillation theory connects eigenvalue counting to zero counting. Eigenvalue counting is the second perspective on the IDS, and zero counting is what we will investigate further. Okay. Okay, so that's what I've explained twice already. So we label by the constant value of K in a gap. And the point of gap labeling theory is to characterize the possible gap labels. All right. So here's Russell Johnson. He's one of my mathematical heroes, and I find that he was totally underappreciated. So therefore, I'm very happy to advertise his gap labeling theory as often as I can. So he unfortunately passed away in 2017. And the paper I will talk about is from 1986. Well, yes and no. So Johnson's paper is from 1986, but really everything I'm saying is in this paper. So this is a survey that Jake Philman and I wrote. I don't remember when, 1 or 2 years ago, but really it was prompted by this memorial volume for Sergei Nabokov. And so as you see here, this survey has 50 some odd pages. So of course I will not be able to explain everything that's here, but I'll explain many things. So I will definitely define the Schwarzmann homomorphism, state the gap labeling theorem, and actually prove it. And then I will talk a little bit about quasi-periodic potentials and a bit more about these affine torus homeomorphisms. So like I said, I will prove some things. I cannot prove everything. So the things I don't prove, you can either consider exercises or you go to the survey and you can find proofs there. Okay, so it's on the archive, it's accepted, but it hasn't appeared yet. All right, so this is my summary slide. So, I mean, you may not be able to see summary of Johnson-Schwarzmann gap labeling. So I will show you this slide twice. I'll show it to you now as a preview of what's to come. And then I'll do all these things that are promised on this slide. And at the very end, I'll show you that slide again. And hopefully you recall that we talked about each bullet point, okay? So here are the bullet points. So the gaps of the almost pure spectrum can be labeled by the constant value of the IDS in the gap. Oscillation theory connects eigenvalue and zero counting. I haven't told you zeros of what, but I will explain that. So once you sort of say, I want to take this correspondence seriously, then you know that the eigenvalue counting, of course, is related to the IDS. That was 2 slides ago. And this zero counting really is related to the so-called rotation number, which also is a fundamental object in this general theory of these operators. Okay, so now that you're really thinking about the rotation number, the key question comes up again, right? So the key question that prompted this picture was, what is special about energies and gaps? And I said here, well, you can alter a characteristic function that is discontinuous to a continuous function. That's special about energies and gaps. You can't do that if the energy that you're jumping at is in the spectrum. So in this perspective here, what's special about energies and gaps is, in Johnson's terminology, exponential dichotomy. In more modern terminology is uniform hyperbolicity or dominated splitting or whatever you want. I'll explain what exactly it is that you have. But this is what's special about energies and gaps. And so this thing that's now called Johnson's theorem really is the primary result in this 86 paper. The gap labeling is a corollary. So really Johnson's theorem is the main point. Johnson's theorem really is the statement that energies and gaps can be characterized by uniform hyperbolicity, exponential dichotomy, and so on and so forth. So once you have that, you have these stable and unstable sections for energies and gaps. Okay, and so once you have them, you do a little bit of trickery. Well, there's some interpolation that you have to address, which I will explain. But then you have an object which is exactly tailor-made so that it can be plugged into the Schwarzmann homomorphism, which is this purely topological object that has nothing to do with spectral theory. You plug in the stable section, for example, its interpolation into this homomorphism. The homomorphism spits out a number, and that number will be the rotation number at that energy, which is related to the value of the IDS, and now you're happy. So that's really the gap labeling from the perspective of Johnson. Okay, so the reason why I really like this approach is that you can compute the Schwarzmann group explicitly for many examples of interest. And so, for example, there are some interesting cases where the group is trivial. What do I mean by trivial? So one observation is that Z is always a subgroup of that group. So you always have Z. Sometimes you have more, sometimes you don't. So you would say if you don't have more, that's sort of the trivial case. It's just Z and nothing else. And so this will actually appear in some cases. And then you'll say, okay, it's Z, so what? And then you remember that a gap labeling theorem tells you that the elements of the Schwarzmann group correspond to the values of the IDS and gaps. But the IDS is 0 to the left of the spectrum and 1 to the right on the spectrum and grows on the spectrum. So therefore, at each interior gap, the value is strictly between 0 and 1. Non-integer. So if the Schwarzmann group is Z, you have no gaps. And like I said, in really interesting examples, you can observe that the Schwarzmann group is Z, and then you're shocked. That means that for all Schrödinger operators that you can define over this dynamical system, the spectrum is connected. It's crazy. And I think this really is a more recent realization. I mean, this whole formalism is from the 80s, but these simple observations are more recent. Okay, so for other examples, you get much more than Z. So for the almost mature, you get Z plus alpha times Z. So now all the values strictly between 0 and 1 are basically K times alpha minus its integer part. So this is these are the values that the IDS will take on gaps of the almost mature, for example. And then you can ask yourself, well, these Ks correspond to these colors. And suppose you have Z's worth, a Z worth of colors. Do I see all the colors? Right? So this is sometimes called the dry time Martini problem. Are all gaps open? Right? I know that the IDS on a gap takes the form K alpha minus integer part, but for every K, can I find a gap? And so this is a question that you can ask once you have all these labels, these elements of the Schwarzmann group. And so then the final piece to the puzzle is to ask yourself, if you know what the labels are, can you show that they actually appear? And results are typically of the nature that the answer is yes for a generic function. So what does generic mean here? Remember that my sampling functions are continuous functions. So by generic, I mean a dense G delta set of continuous functions on omega with values in R. So, right. So that's the plan. And now let me check the time. Okay, that's good. All right, so let's go. So we'll do all these things. So we start off with Johnson's theorem, exponential dichotomy and uniform hyperbolicity, right? So that's the question, what is special about E's and gaps? And the answer in this discussion is there is an exponential dichotomy, which has also made an appearance already. Okay, so transfer matrices. You've seen these before, yes? Okay, good. So this is how they look, right? So really what you do is you take this E minus F minus 1, 1, 0. So which F? Well, you evaluate F at some iterate of omega, and you form these products. So, I mean, sometimes you start at omega and run through T to the M minus 1 omega. But actually, I mean, if you really map the solution vector from 0, 1 to n plus 1, you actually have to start at T omega. This is the right transfer matrix. Anyway, so if this is not precisely the one that you had in mind or that you have here, then you just shift by 1 and you're happy again. All right, so these are the transfer matrices. So uniform hyperbolicity corresponds to uniform exponential norm growth, but really a uniform exponentially, an exponentially growing uniform lower bound on the norm. That's what it is. Okay, so in formulas, it means that there is an exponentially growing object. So the C and the gamma are positive, so that all norms are at least that much. Okay, so for all omegas and for all n's, F is fixed here. E is the energy that we're trying to understand. I have this lower bound on the transfer matrix norm. Okay, so this is uniformly hyperbolic behavior, but you're really interested in whether for an E you have it. And so you collect all the E's for which you have uniformly hyperbolic behavior for the associated transfer matrices in the set UH. So that's one thing that's a little bit easier to define. Exponential dichotomy actually also showed up on Lingoy's slides, is the splitting that is both invariant and with appropriate estimates. So again, you ask for a given energy whether you have something, and the something that you're looking for are again constant C greater than 0, L greater than 1, and continuous maps, stable and unstable, from omega to the projective line. So those are just the lines in R2 through the origin. Okay. So the point is that these transfer matrices here have determinant 1. So if you take a line through the origin, then for each element in that, so anyway, you apply this matrix to that line and you get a new line. So therefore you can view this map here as a map that's defined on the real projective line. So therefore you can write down these things here. So these maps should have two properties. There should be invariance and there should be this suitable decay. So the invariance just means if you look at the line that you have at omega, apply the transfer matrix to it, then you are transported to the line that you have at T omega, and that you can of course iterate. The same is true for the U guy. And what's the difference between S and U? So this just means both of them are invariant. S and U corresponds to stable and unstable. Stable means that you have decay under forward iterations, and unstable means that you have decay under backward iterations. Okay, so you take, for example, the stable guy. So lambda S of omega is a line. You take a vector in that line and you apply these transfer matrix for positive n's to it, and the vector will be mapped to vectors that decay exponentially like that. Okay, and for the unstable guy, you want to have the same thing but going backwards. So you have negative n's or minus positive n's. Okay, so I think Jake talked about this. Linguy had it on the slides. So this is what in Johnson's discussion is referred to as exponential dichotomy. And I apologize for that, but I will just refer to ED. Okay, so these are the energies for which you have an exponential dichotomy. And so this theorem that's called Johnson's theorem tells you that this is precisely something that you can use to characterize whether you're in the gap or not. So an energy is in the complement of the spectrum if and only if you have uniformly hyperbolic behavior, if and only if you have an exponential dichotomy. So that's the property that you can exploit. So again, this uniform hyperbolicity is maybe something that sort of more recent times, well, anyway, so this is something that you just like to study for various reasons. But for our discussion, exponential dichotomy is the point. The point is because you really get these continuous maps. That's really the starting point of Johnson's gap labeling theory. So I'll work with this property that I have for energies in gaps. Okay, so Jake tells me that he discussed this theorem, so I hope you remember that. I will not prove this theorem. I will spend my time on the gap labeling application. Okay, so oscillation theory. I don't know if Jake discussed it. I didn't ask him. Maybe he proved it. Okay, great. Okay, oscillation theory, like I said, connects eigenvalue counting and zero counting. Now, what do you count? So for eigenvalues, you take an energy level and then you count the eigenvalues either above or below, depends on what you want to do. So And this is for the IDS exactly what the second approach actually asked you to do. You took an E and you counted the eigenvalues below and then sent to n to infinity. And this really should converge to K of E. So that's something that obviously is relevant for gap labeling because it converges to the IDS. Okay, so which zeros do we count? So since he proved it, I can go through it a little quicker. So, okay, so maybe I should write down. Okay, sorry. I'm looking at the associated difference equation, right? These solutions of the difference equation are precisely the ones that you can describe with matrices of this form here. So look at solutions like this and start off with the values 0 and 1. So it's a second order linear difference equation. You prescribe two values, you compute them all. So this determines the solution. And now you count zeros. Zeros of what? There could be no zeros at all. So you linearly interpolate UE between values. So for example, between 0 and 1, you run in an affine way from 0 to 1. Okay. And then you keep going like that. You have these points and then you just connect them with a zigzag line like that. Okay, now you have a potential for zeros and you count them. Okay, so for each n, you count the number of zeros of this interpolated guy in the interval from 1 to n plus 1, and to note that by Fn of E. Okay, E is the parameter on the right in the difference equation, n is the length, or rather the length of this interval here, and you count the zeros. And so the oscillation theorem zero counting is related to eigenvalue counting. So here are the zero counts, right, defined here. This is a zero count, and this is an eigenvalue count. You count the number of points in the spectrum of this n by n tridiagonal matrix that lie above E. Okay, so that's what oscillation theory provides. And obviously, this matrix here has n eigenvalues. For the IDS, I need to count the eigenvalues below E, but that number is, of course, n minus that number. Okay, so it's really equivalent modulo this energy inversion, or however you want to describe it. It's basically the same thing. Yes, exactly. Yeah, you can also call this the Sturm oscillation theorem. Yes, but it is exactly that. All right, so here's the takeaway message. So if the formulas look awful, just remember this take-home message. All right. So now, IDS, eigenvalue counting, oscillation tells you zero counting. So now, how does that relate to anything? So the first thing that you do is, well, I had chalk, right? Okay, well, there must be more chalk. Okay, so now you look in this plane. Okay, so you look at this 2 vector here that of course is in one-to-one correspondence with the solution, and that will be a point in this plane. Okay, so maybe here. So this is a point if both values are positive. Okay, so now you increase n by 1 and you get a new point. Okay, so maybe the next point after increasing by 1 will be here. I don't know, this will be the point that corresponds to un plus 1, un plus 2. And then you keep increasing n, you get a bunch of points. And what does that even mean? Okay, so how does that relate to a rotation number? Nothing is rotating here, just have a bunch of points. So the interesting thing is, again, you have to interpolate, and you have to interpolate in a slightly smarter way than here. So this is a really pedestrian way of interpolating. So there will be a very nice interpolation that allows you to continuously run from here to here. But now if you do this for the sequence of points that you get, all of a sudden you can actually ask if something is rotating so many times around the origin. Okay, so the next step in the program is to find a smart way to interpolate between these points, and then to wonder whether this has a well-defined rotational property around the origin here. Okay, so. Okay, sorry. Yeah, exactly. So in order to do this appropriately, we need to suspend the dynamics. So suspension here refers to continuous interpolation. So how do we continuously interpolate? So we have our dynamical system omega t, which is a discrete time dynamical system, right? The dynamics just given by t squared, t cubed, just integer powers of t. So this power n is your time parameter, n takes values in z, so there you go, it's discrete time. So we want to replace this or interpolate in such a way that you get a continuous time dynamical system. And so for that, you have omega here, okay? So t will just really map from here to here. That's what it will do, right? So in this space omega, t will map you from little omega to t omega. That's what it does. This is in one time step. Okay. So now I want to declare what my continuous time dynamics actually is doing between times 0 and 1. I know at time 0 it's at omega. At time 1 it's at t omega. But what do I do at time 1/2? The answer is, at least in this approach, is you flow vertically. Okay, so you flow in time 1 up to here. So now you look at omega cross 0, 1. Okay, you take these unit time intervals and basically write them above each little omega. And then from time 0 to time 1, you just flow vertically like that. Okay, at some point you reach the top. So this here is omega cross 0, and this is omega cross 1 in this product. Okay, so I will arrive at little omega comma 1. And so that guy, I want to immediately, with no further time elapsed, send down here. Or in other words, I'm forming omega cross my interval, and then I have my big omega here, my big omega here, and then I glue it back down here, but twist it according to the dynamics, which some people refer to as the mapping torus. It's really like a torus construction, but it's not that you just identify, you actually twist according to t, right? So this point, omega comma 1, is immediately sent here to t omega comma 0. So that's what I mean here. You take this product and then you identify these 2 points. So that produces something like a torus. And then, of course, you can keep flowing, right? So right now I've sort of told you what you do in the first time interval of length 1. But if you keep flowing, you can also look at points of the form omega comma t. But you know after each amount 1 of time, you come back. And so really, if you do it for, say, n comma 5 times, then really you end up where you should end up, namely you apply t n times to omega, and you're left with 0.5, right? Okay, so now you have a continuous time dynamics on this torus, mapping torus. I will denote it by t bar super t. T now is in r, so that's my time variable, it's continuous. So I've suspended the dynamics. I will also suspend the measure. So my mu was a measure on omega. I need a measure on this product here, and I take the product measure with a normalized Lebesgue measure on 0, 1. So that's my mu bar. Okay, so now I have this object, right? I have this omega cross 0, 1, and identify points in this way. That's my new space, which is denoted by x. That's called the suspension of the dynamics or the mapping torus. Okay, so this will be the x here. The x is that torus. Now I take my mapping torus and I look at continuous functions from it into the circle. So this is what I referred to before as what happens now has nothing to do with spectral theory. I have this space, I look at continuous functions into the circle, and I ask what they do. Okay, so I look at the continuous functions, and then I identify those that are homotopic to one another. So the C# are the homotopy classes that I get in this way. And then you can check, this is not difficult, so exercise, but it's also explained in the survey, that this C# is a countable abelian group. So this is maybe one of the reasons. So right, if you have these gap labels, I mean, the first thing that you note is that, of course, each spectrum has only a countable number of gaps. That's clear. However, much more is true. So the values for a fixed spectrum will be a countable set because each gap has a label, namely the value of the IDS on that gap. I have countably many gaps. So the labels that I see for a given spectrum form a countable set. Okay. However, I'm allowed to vary my sampling function. This f, right? My potential is of the form f of t to the n omega. And so now that I'm allowed to vary f, for each given f, I have a countable set of values of k. That's countable, but now I vary f through all continuous functions. It's absolutely shocking if you hear for the first time that the union over all f's of the labels that you see is still countable. And really the reason for that is that, right? So again, this is a simple exercise, but it is the reason why the following surprising result is true. There's one countable set that serves as gap labels for all potentials that you can write down. That is absolutely not a countable set, and it's gap labels. All right. So, okay, very good. Let's see, let me try to see. Okay, so let me take these 2 minutes to just define the Schwarzmann homomorphism. All right, so I take a continuous function. So now I'm back here. This was just to introduce the homotopy classes, but now I actually take just a continuous function. And so now sorry, I plug in my, oops, this should be T bar, right? So I have my continuous time dynamics on the mapping torus. And so this is just a flow on the torus, but phi is a function on this torus. So I can just evaluate the flow using my phi. Okay, so I denote that by phi sub x of t. So this now is a continuous function from R because t is in R to t because phi is t valued. And now this function from R to the circle I can lift, right? If you map into the circle and move around the circle continuously, then, I mean, you can either move like this and move back, or you actually honestly move like this. And then you want to count the number of times you rotate, but in the circle, you keep forgetting. If you just look at the circle and wait 100 minutes, you don't remember how many times you've actually rotated. For that, it's good to lift the function and basically see how high up you can go. Okay, so this is what you do here. So there is a function from R to R that projects back to your function. Right? And so that's just what it is. It's a simple exercise to lift the function from R to T to a function from R to R. And that's what we do here. And so now we have these lifts. They now have a potential for growth, right? If you want to count how many times you rotate, you have to ask if there's anything that grows on the order of T, right? If after 10 time units, I've rotated 5 times, then I want to be basically at height 5T. Right? And so the question is, as I send t to infinity, do these ratios converge? And if they do, this really has the interpretation of a rotation number. It's the average number of rotation per time unit as you send t to infinity. And the reason why this limit exists is, again, ergodic theory. So it's the ergodic theorem. The limit will exist for mu bar almost every x. Okay, so now the next thing is another exercise in simple homotopy properties. If you have 2 homotopic phis, then these limits will be the same, okay? Because if they stay close to one another, they have no choice but to track each other, right? Because if one rotates, the other one cannot not rotate. It has to also rotate if it stays close. And so the limit will actually be the same. And so that's good because now we can actually descend to a map on the set of homotopy classes, and that's the Schwarzmann homomorphism. Remember, this is a countable abelian group. This is a homomorphism, and so its image will be a countable subgroup of R. Okay, and so I will stop here only after flashing the theorem, which I will prove tomorrow. That's the first thing I'll do tomorrow. So this Schwarzmann group, the range of the Schwarzmann homomorphism, right, serves as an interpretation of the values of the IDS and gaps, okay? So for each sampling function, for each energy outside the corresponding spectrum, the value of the IDS at that energy, of course, has to be between 0 and 1. That's the property of the IDS, but it's also in this countable subgroup of R. Okay, so again, in the almost material case, you'll get Z plus alpha Z. And so that intersected with 0, 1 gives you the labels in the almost material case. And so my goal for tomorrow is to explain why this theorem is true, and then to compute Schwarzman groups for several examples, some of which will have Schwarzman group equal to Z, thereby proving that the associated spectra are connected. Thank you. Sorry? Well, I mean, the value is the same, but the point is you compute the possible values using topology, right? You combine the two things. You compute the Schwarzman group, and you show that the rotation number is in a Schwarzman group, and therefore you put obstructions on the structure of the spectra. Yes, it is the rotation number, but the point is that the values of it can be computed explicitly using this formalism. Okay, so I should go back. It's here probably, right? No. Okay, so let me quickly go there. Sorry about that. So it does in some sense. So where's Johnson's theorem? Here. Okay, it does. This is really important. Okay, because right, you want to have, if you're not in the spectrum, how do you produce uniform hyperbolicity if your measure is not fully supported, right? Take the full shift and take a finitely supported ergodic measure. It's ergodic, but the energies and the gaps of this periodic thing could definitely be in a region where the co-cycle on the full shift is not necessarily uniformly hyperbolic. Oh, I see what you're saying. Yes, okay, yeah, I know what you refer to, yes. Well, I mean, if you don't have ergodicity, you don't have the IDS, you don't have natural labels. Okay. So yeah, so no, this sounds like something that can be done, but it has to be formulated properly, yes. But you're right. So in some sense, if you have sort of Jenga's result, you can plug that into whatever you can connect to spectral properties that you're interested in. Fake IDS, I don't know. Yeah, no, but yeah, you're right. I mean, that's true. So this theorem really does extend to a deterministic version. That's a result of Zheng Zhang. Yeah. So the important thing is that you do have this identification here. So you don't, I mean, while you do get topologically a torus, it's a twisted torus, which actually contributes to the value of the limit that you're taking. Right? So, I mean, so let me go there again. So you do plug in the dynamics here. So here at this point. So when you form the Schwarzman group, you actually use the dynamics. Yes, it does not, but the Schwarzman homomorphism does, right? Because it's the limit of this guy. The steep sharpening, yes, does not depend on the dynamics, yes. It relates to the cohomology of the space. Okay. No, but what do you mean? I mean, it's the abelianization, right? And so the other thing is, right, the fundamental group is you take images of circle into space, but here we have maps from space into circle. So that's why the arrows flip. Yeah, there is a relation. So the first homology group is the abelianization of the fundamental group, and cohomology is dualization of homology. But anyway, so I think the point really is it's useful as soon as you can actually do explicit calculations. The perspective that you take in order to compute these groups is really up to you. But what really makes it interesting is when you, first of all, get an explicit description of the group. And then the follow-up question is, once you know what the group is, do I have gaps for each of the elements in the group where that element is taken by the ideas? Those are sort of the questions that you then ask. So I think that is probably something that you can generalize, but what you cannot generalize is this Johnson theorem, right? So, I mean, where is it now? Yeah, exactly. I forget where the Johnson theorem. Yeah, exactly. Where's Johnson's theorem? It's gone. Anyway, so there's no exponential dichotomy. There's no there's no co-cycles. In higher dimensions, you basically, okay, so in higher dimensions, you don't have a finite dimensional solution space. And so then you don't have these finite dimensional transfer matrices. And in terms of the transfer matrices, everything is phrased here. So I don't know. So yeah, so I think just the sort of the suspension, I think you can generalize, but then the question is, what do you do with that? So I think the subsequent steps really are one-dimensional arguments.